This is calculating right here. Right here.
But now the calculus.
A person goes like tacos and just trustworthy.
You need
So I got, you can literally put anything on taco, like, put gummy worms on a taco.
Okay, yeah, like some of them.
I love nachos, I agree. And they don't break.
Wait, can I have my coins?
Oh, yeah, they're right here. This is your pile. Is Cal still here? This is his pile.
No idea.
Well, if you see him, tell him he's got 3 coins back here.
Yeah, no fun there.
All right.
I just don't like tacos.
Tacos are good, but they do fall apart.
You like burrito.
Yeah.
And then you take your tortilla chips and in the wrapper, you get the stuff that fell out of the taco.
Ah,
You like burritos.
Oh, yes, that's what I get from before.
Okay.
Whenever we get like bows or something, I always get like.
Those burritos are pretty good. Yeah, what I get from Chipotle is I get a burrito with
there we go.
either, I really like the pollo asado, so I either get pollo asado or chicken or veggie. Pollo asado is basically just like the city.
That's good stuff too.
Really.
Just slap.
But anyway, I put,
And then
I put lunch,
again.
white rice, black beans, lots of cheese, medium salsa, lots of corn salsa.
You have very specific, you have very specific needs when it comes to your Mexican food, do you?
Well, I just like that. I like this one.
You like the corn.
The corn salsa.
I have a friend who thinks corn is scary. Like it kind of grosses him out and he doesn't, he doesn't ever want to see corn and it's funny.
Right.
Who doesn't want to see corn?
Father Joe doesn't like corn. It freaks him out.
Sometimes
For real. No, But just like Father Darren thinks that avocados are the devil's fruit. He doesn't like them at all. So he's wigged out by them.
I like corn and.
I love guac so much I could never.
I know, me too. I would have a problem with that.
I like corn and corn.
Yeah, but my friend Joe does not do corn. He's like, ugh, when he sees it.
That's understandable.
Not like he doesn't like the taste. The whole concept of it freaks him out. Okay, so I made a little thing with your names on it so I can give you money.
I also like their queso.
Take it out.
Yeah, true. It's not very big. You can just pick it out. Oh, we got all that settled in? What the world are you doing? You need a haircut? All right, so
Yeah, I did it right.
gonna do a lot about mapping and whatnot today. So
Wiggly line.
we will start with latitude. Very nice. I see. You can keep it. Or is that, that's not extra credit, is it? You just show me what's in your binder? Yeah. Okay, I'll have the answers up at the end. Cool, awesome. All right, so we're gonna talk latitude and longitude. We're gonna talk about what they are. We're gonna have a nice little easy clue to help us remember which is which. So let's talk about latitude first. So our lines of latitude here, okay, we call them parallels because, oh, what do you know? They're parallel. Now, longitude lines are not gonna be parallel. Farming on bunch of apple there. Last week I didn't eat and starved when you left. Okay, so they run east to west, y'all can see. And they measure the distance north or south from the equator. So about how many degrees north or south is New Orleans? Anybody? What you get, Pepper?
About 30 or 40 degrees? Yeah, I think 30.
About 30 degrees, which, north or south?
No.
Bingo, Pepper. All right, so about 30 degrees north is New Orleans. Now, if you were going past the equator, the other direction you'd be saying what, however many degrees south. So they're parallel to one another. They never meet. You can see that the ones at the top are the distance all the way around is shorter than the equator, which is going to be the longest line. Like you take string, right? You do that around the globe, but they never meet each other. Now they are going to cross at the prime meridian at right angles. Does anybody know on here? Can anybody describe roughly where that prime meridian is? Alex? Oh. Britain? Yeah, but on this picture, James.
About where the
Numbers are.
Africa, if you look at Africa sideways and you see the dinosaur, where the neck of the head is.
That's a good one. Yeah, both of you guys are getting it right. See where the
Yes.
numbers are listed? That's roughly where you're gonna find your prime meridian. And Alex is right. It does go through Britain. It goes through Greenwich. We say it
That means degrees of Greenwich.
Yeah, we say it Greenwich, even though it looks like Greenwich, because I don't know, English people are strange. They do that all the time.
Hey, they gave us the office, I'm not gonna complain about their.
True.
I think it's everyone that in the islands that isn't British.
Yeah, they come up with interesting pronunciations, but they're not the only ones.
Yeah.
I mean, there are some strange pronunciations of cities and towns around America too. So they lie in planes that cross the Earth's axis at right angles. So if the axis, if you look at the globe, is gonna be basically that pole that goes pole to pole. There's a rod in there, right? So they cross at right angles, which you can see pretty clearly if you imagine a line right there where the numbers are. And they get shorter towards the poles with only the equator the longest, making your great big circle. So they're horizontal. So how many degrees? You have to think of them like horizontal. Because for whatever reason, we typically, well, I know the reasons because of who did it the first time, and it's become sort of the way we do it, the standard. But we tend to draw our map north at the top, south at the bottom. That's kind of the way we've always done it. There's not like a good scientific reason why, it's more of a social reason why, and it had to do with who discovered things. They put themselves on the top of the globe instead of on the bottom of the globe, right? We're on top. So how many degrees is the equator? Bailey?
0.
It is 0. It is 0 degrees. All right. So, and the poles, how many degrees are the poles, Jeff?
90.
90. Okay. So, lastly, does anybody know what you need?
I forgot to get.
Oh, yes, here, here's your 3. Your 3 are right there. Later, dude. All right, so about how many kilometers is a degree? Do you know, Bailey?
111.
Bingo, 111. She gets it right because she's got her binder in front of her, don't you? That's the point. Good job. That's what you're supposed to be doing. 111. Okay, very good. Now, let me ask you before we go to longitude. Longitude lines are going to go this way, right? More like this than like this, really. Think about where that 111 degree might fall, all right, on one of those lines. So here's your longitude lines, all right? So we call them meridians, whereas we call the latitude lines parallels. We call these meridians, and they run north-south. We kind of think of it as up-down. So they measure the distance east or west of the prime meridian, which you can see right there. So in this one, where's the equator now? Where do you see? Do you see anybody who hasn't answered yet? See it? You're thinking about it, Mitchell. Where's, you see where it is? The equator?
Liam.
Oh, we left. Liam, I'm sorry. You guys both have on a hat today and I'm trying to get your names straight still. Liam, okay, can you tell where the equator is? No? No. All right.
Where the numbers
Where the numbers are. All right, Piper's got it. Where the numbers are. So yeah.
I kind of the entire time.
And you're gonna get 900 of them right, you know it. So they cross the equator. So they cross the equator at right angles, right? And they lie in planes that pass through the Earth's axis. They're equal in length as opposed to the parallels. Parallels were not equal in length, right? The ones closest to the equator were smaller. The ones closest to the poles were smaller, closest to the equator were bigger. But these guys are all equal in length because it's like you're taking a yarn and you're wrapping the globe this way, right? So they, we think of them as being vertical, whereas we think of the parallels as being what? Horizontal, right? So your prime meridian is how many degrees? All right, Liam.
0.
Prime meridian is 0 degrees. Very good. You can see that right there. Now, all meridians are going to converge in one place. Do we, or 2 places? Do we see where they are? All right, Alex.
North and South Pole.
North and South Pole. All right.
Not necessarily the magnetic poles anymore, since the core is shifting, which shift the
Right.
poles.
Very good. Yeah, our magnetic poles and our geographic poles are not exactly the same. And we will get to that in a future lesson. But yeah. All right. They're semicircles or ellipses. They're shaped like this, not like this.
They're parentheses.
Yeah, they are kind of like you put parentheses around the Earth, but the space between two. So this little shape, if you were to take it like a little section of an orange, right? This is an ellipse, this shape from here to here. So it's not a rectangle because it's wider here. So 1 degree varies from how many kilometers to how many kilometers, Bailey? 0 to not 180, but 111. Where would you get the 111? Jack?
Oh, wait.
Oh, I don't know. I don't know.
The equator.
Okay, at the equator. And where would you get the 0? Jane, oh, no, Chloe,
The pole.
at the poles, right? Okay, cool.
All the same,
So
they all occupy the same.
what's your answer, Jack?
I don't know if this counts as a brownie point,
No.
but there's like an extra space between the 0 and the KM. I don't know.
That's just. to make it-
No, it's because of the little block that was on it has to be a certain size, See?
Okay.
but good
But the
try.
other one was-
Really good try. Yeah, that's because it's bigger. Really good. I had to make the block big because if I made the block small, then you'd know how many digits was there. See, so I have to try and outsmart you somehow. So why does this distance vary? Who can give me an explanation type of answer? Let's see. All right, James, you go.
Hold on, this shit.
I'll get a carrot. Gotta swallow my carrot.
Why are there so many trees in front of the window?
Weirdest thing ever.
Wait,
So
I
the
wasn't here
distance
today.
varies because
You're looking
As
to go
a-
with that for
as a
now.
Alex, who's answered?
down into sphere, so.
Mm-hmm,
You got the
right,
different things.
Right.
At the top and at the bottom.
very good. All right, one now.
I argue the weirdest thing ever was Cole pointing out Professor Dave's chest hair, but that would be.
That was
my-
strange too.
That would be my throw up for the strangest thing ever.
I still go back to the weirdest thing ever.
Oh, fucking some beast.
Same concept of whacking bees was the time, the first earth science, so this 5 years ago, when Henry disappeared from class, and I love this kid, and then came back 10 minutes later and sat down and said, Miss Danny, your toilet seat is so hard, or something to that effect, or so small. And we all were like the whole class just stared at him. It was a random comment. It was great. It was a great comment. All right, so here's your trick for remembering latitude and longitude. You ever seen this trick before? All right, so, there's the little Rico. Engrave it in your brain. Keep this one in your brain for your life. It's important. So here's what you do. You think of a ladder, okay? You envision a ladder. A ladder has these poles that run up and down, kind of like the north and south pole kind of go up and down. And that long part of the ladder, you think of as longitude. It runs vertically. It goes from top to the bottom of the ladder. So longitude along, right? It's long. Now for latitude, what makes those two poles, not poles, but a ladder? You put the rungs in and the poles become a ladder. So if you think about the steps or the rungs, those are your latitude. That's what makes it a ladder. So that's a good way to kind of get it in your head, latitude and longitude, so you don't confuse them ever. If you remember a ladder, you'll be good. Mhm.
I'm just thinking of a giant ladder shaped like two longitude lines,
Yeah.
and it just shaped like a giant banana type thing.
Yeah, because it's like this, you mean like that and curved? Yeah, would be a really strange ladder.
Ladder.
It would be something for like the, what are those, the ninja places, the parkour ninja course? Yeah, it would be like that. It'd be fun. Yeah, kind of like that. Yeah, American Ninja Warrior. That's a show I don't watch, but if I turn it on,
I watched,
I can't look away.
I watched the.
It's like a train wreck. I can't look away.
I watched the original Ninja Warrior, like the Japanese version. and
Yeah.
It was so great.
That's
I loved it
hilarious.
so much.
Japanese game shows are the best, the
It was
absolute
like
best.
Like an actual like parkour. It was
Right, right?
on G4 and all these things.
Crazy for sure. All right, so the international date line. Okay, this is an odd little thing. So it's an imaginary thing. It's not a real thing,
Great.
but it's something we've developed because obviously as the Earth rotates, so the Earth does two things as far as letter R's go. It rotates and it revolves. What's the difference? All right, Alex.
Rotates, is it spinning in place? Revolving, is it spinning around the sun?
Right, okay.
Rotation creates day cycles,
Mhm.
and revolutions are part of what causes seasons, along with tilting of the axis.
So the axis, right? Very good. You're gonna blow through some of this stuff we're gonna do in the next couple weeks for sure. So yeah, that's exactly right. So it's this imaginary thing. It's drawn north-south, and mostly it cuts through the Pacific Ocean. It's about halfway around the world, or close to 180 degrees from the prime meridian, which cuts through, as we already said, Greenwich, that is
Greenwich,
smelled like Greenwich, right? All right, great. And the date line shown on most maps is one drawn by the British Admiralty in 1921. And that's the history we have on it. So it interestingly has no force in international law. You can do whatever you want. You can change it if you want. If you're an island in the middle of that and it cuts through, you can say, well, we're gonna be on this side, or we're gonna be on that side. So it's a line of convenience. So any given day has to start and end somewhere and is not recognized as a legal entity. It has no international status, was not defined at the 1884 Prime Meridian Conference in Washington, DC, or by any treaty according to the Royal Observatory in Greenwich. So it's just kind of this imaginary thing. So it zigzags. So the reason it's going to zigzag is because you've got countries that it cuts through or to the left or the right of when they're doing north, east, or west of, when they're doing trade with another country that's east or west of them. Can you imagine that you're doing your trade and it's, so if Jack is one island and Sky is another island and they trade, okay? So on Sunday, one of them is going to be chilling and resting. And what's going to be happening to the other one?
Or
So let's say Sky is on the eastern side of the international date line, and Jack is on the western side of the international date line, and they're trying to trade. What does that mean to them? Like, how is that going to affect their business, for example? Think about it.
there's gonna be multiple. It's gonna be one day each where one of them's working and the other's not.
There'll be two, because on the opposite end of the week, right, you're gonna have
One
2
each.
days. Yeah, one each. Each country is gonna have one day where it's not working and the other country is. So instead of having a nice 5-day work week, they're now down to like a 3-day work week, and that's really not convenient, right? Plus, let's say that Liam and Piper live in the same country, but the international date line cuts between them. And they have to go to school. Piper has to go to school on Liam's side of the international date line. Like, is that going to work? That's not going to work, right? So that's why it takes these little zigzags. So the midway point actually crosses very few bits of land. 3 islands that are part of Fiji are the only islands actually crossed by the 180-degree line. And then we get this phenomenon here of gaining or losing a day. So the circumnavigator Ferdinand, when the Portuguese explorer Magellan, remember Magellan went around the whole earth, circumnavigated, and his crew returned from their 16th century westward circumnavigation of the globe, they discovered they somehow lost a day. Anybody done that when you're traveling? You lose part of a day or gain part of a day? Yeah, it's interesting. All right, so hopefully this doesn't, it jumped around a bit earlier, but hopefully it won't. She does a good explanation of having a really long day and how you can make that work.
Oof. I've literally had the longest day ever.
Good old British accent.
I think she's an Aussie.
Hello, Maddie, a really long day. Sorry.
She has a Union Jack.
Watermelon? No, actually.
Yeah.
Watermelon.
Aussies have that
I
too.
was just saying, but I had to get up at 3 a.m.
Maybe she is a weird British. I don't know what she is.
And that didn't start it.
British accents have their own accents.
So now I'm told that I'm basically a time traveller. Care to explain? Sure. So we've all had days that feel like the longest day ever, but that got me
That
thinking,
sounds great.
how could I literally have the longest day ever? What would I have to do? And then it got me onto the very confusing subject of global time zones, the international date line, and time travel. Imagine this watermelon is our planet. It's a rough rotating sphere, and it rotates in an dude, lady.
She said water like.
160 degrees in 24 hours, which is the time it takes from sunrise to sunrise. Knowing this, we can work out how far the world travelled in 1 hour. So if we take our 360-degree rotation and divide it by 24, we get 15. So every hour the world rotates 15 degrees. And we marked it using vertical lines of longitude, also known as meridian. And quite handily, this watermelon here, a vein, will represent those quite nicely. 24 vertical meridian, each one marking 15 degrees and 1 hour's worth of time. It's all very well having 24 1-hour zones on our planet, but we need them to start somewhere. And this is where the Greenwich meridian comes.
What's your problem today?
It marks 0 degrees, the point where time starts, and it runs through Greenwich in London. The Greenwich meridian, marked out by my beautiful red city dot, was chosen as the starting point of time, 0 degrees, because at the time, 1884, 72% of the world's commerce depended on sea charts, which used Greenwich as their prime meridian. So this is where it all begins. it's midday in GMT, Greenwich Meridian time. The sun is directly overhead. However, it was midday 1 hour previously, +1 down to the east of our line. So if I just rotate the Earth backwards 15 degrees, we can see here, we find midday on +1. I then rotate to the east 15 degrees and continue to our -1 line. We find it's not midday till 1 hour later. And this is why we have plus lines of longitude and minus lines of longitude as the Earth continues to rotate in an easterly direction. As long as we know the location of two places on Earth, we can work out the exact time difference between them. LA is 120 degrees away from the UK. If I divide 120 by 15, that's 15 degrees per hour, I get 8. That's 8 hours. So the UK is 8 hours ahead of LA. -1, 2, 3, 4, 5, 6, 7, 8. Now, Stress Maddie called it 3 a.m. If we subtract 8 hours, it was only 7 p.m. from LA. The Greenwich Meridian marks time 0 and enables us to add or subtract hours, so we can work out time differences across the globe. But we need a way of defining exactly when a new day starts. After all, you can't continue to fly around the world in an easterly direction, just subtracting hours as you go. You could lose days, and that's time travel, which is impossible. Yes. There are 24 hours in a day. It makes
Yeah, you're on what?
to start 12 hours or 180 degrees away from the meridian line. So if I subtract 12 hours, we find ourselves at the international daylight. Now, here we have from 12 p.m. till 12 midnight on a Monday. The moment that we cross over, we find ourselves at 1 a.m. on our Tuesday. Tuesday then starts to grow, slowly eating up Monday as the Earth rotates, until eventually we get to Tuesday at 12 p.m. Now, there's only so much I can show you with a watermelon, but this video with better graphics down the YouTube. So the date immediately to the left-hand side of the international date line will always be 1 day ahead of the date immediately to the right-hand side of the international date line. In fact, if you were to go to the North Pole, you could walk around in circles, crossing from day to day. Conveniently, the international date line largely lies in the Pacific Ocean. However, you can see it's not quite straight, as it's been moved slightly over the years to accommodate the needs of various countries. As I'm sure you can imagine, it can be pretty frustrating for two countries to do business with each other when they're only a mere few hours apart but exist on completely different days. For example, come on, girl, talk. These guys could be working away busy on a Monday and only a few hours away, everyone's still chilling over here on a Sunday. But that is exactly what happens with Tonga and American Samoa. Tonga and Samoa are in the same time zone, but are split by the international daylight. That means when it's 5 p.m. on Monday in Tonga, it's only 5 Sunday in American Samoa, but they're just an hour and a half flight away from each other, and near 552 miles. Therefore, if I spent my entire Saturday on Tonga, I could then catch a plane at midnight, and an hour and a half later find myself in American Samoa at 1:30 a.m. on Saturday. I have a whole day again. Technically, my entire day could last 48 hours, and that's just by crossing the international daylight.
I'd love to do that.
Keep trying to watch.
She's a little crazy about there,
Watermelon would be.
Oh, no, sliced it.
Yeah, that's what happens with
Yeah.
a watermelon, like.
So y'all know that I always give you the links to these videos and stuff so that you can go back and look at them when they're not jumpy and it's not as distracting. But yeah, if you cross from one side to the other at the right time of day, you could have a 48-hour day, which is pretty crazy. So let's talk about different types of maps. So you got projection maps. So this is a cylindrical map. You've probably seen this before, all these little perfect boxes. So those are projected onto a cylinder. All right, now, latitude and longitude lines. What are they on this map? How would you describe them? James, you did it. You just said it. Yeah, what's the word for that? Yeah, parallel, right? They're parallel to each other and then at right angles from the other. So that's very good. All right, now, so then thinking about that, this kind of map is designed to help sailors circumnavigate the globe. All the latitude and longitude lines intersect at, Liam,
90 degrees.
90-degree angles. So you can see that nice, perfect little 90-degree, where are you? 90-degree angles. And so an example of this would be a Mercator map. This is a Mercator map. And I'm sure you've seen them before. So their purpose here is really useful for sailors. not as useful necessarily for other types of locations. So then you have conic maps. So this is created by setting what, Liam?
Cone.
A cone. You set a cone over top of the map like that. You project your light down from the center of the globe onto this cone, and then you get distances between regions and areas that are distorted at the poles. But this is good for mapping regions that are primarily east-west, like the United States. Y'all good back there? You guys good? Okay. Primarily east-west, like the US. The US runs primarily east-west, right? We're wider this way than we are longer, right? So this is a good kind of map for mapping this. So does anybody know that, you know,
Are you counting Alaska?
it maybe, yeah, I guess you could count Alaska in that, yeah.
Because I think that might make it taller than.
Distorts it some, yeah, obviously, but it's still east-west, yeah. Alaska still runs more east-west. So do you, anybody know what kind of map this, the most popular conic is? So these are Lambert conformal conic. So that's what this is, the one you're seeing here. And that's really the well-known type. So all the meridians are equally spaced straight lines converging to a common point, which is the nearest pole to the standard parallels. The parallels represented as circular arcs centered on the pole. Spacing increases from the standard parallels. And then pilots. These are really good for pilots. Now, when you look at when you're on a flight and they show you the map with your actual flight plan, like where you're going, it always looks like a curve, right? Because the Earth is curved. Never looks like a straight line. It always looks like a curve. You look at any of the little flight maps, like in the little Delta thing or whatever. And so that's why this kind of map is really useful for pilots, because the aeronautical charts are actually based on this Lambert conformational conics type of map. And because a straight line drawn on this map gives a good approximation of the actual distance because of the curve. So you have to kind of envision the way the map is projected and how if you went from point A to point B on that type of projection, it would actually reflect the curve as far as distance from one place to another. So it's great for pilots and it's the kind of thing that they use. So other projections would be this one here. So this one is planar or azimuthal. You'll see it described both ways. So this is projected onto a plane, obviously. I can take that one. So it shows the distance and directions accurately from the center point, but it distorts shapes and sizes elsewhere. So I mean, look at how crazy that. I mean, that's woo, right? Very distorted looking. So it provides provides navigators with an opportunity to find minimum distance from one point to another. So examples of this would be something we call stereographic or mnemonic, which is a projection that displays all the great circles as straight lines resulting in any straight line segment, blah, blah, blah. So just let you know, this is a planar one. So instead of taking the cone, they set it like a plane. So it's definitely a different sort of image that's projected. So another type of projection, anybody seen one of these before? Where they kind of chop the globe up into these little sections and spread it out like that. This one's relatively accurate for distance and actual shape. So this one is a pseudo cylindrical or an oval. So they wrap it on a cylinder and then they project the light through the globe onto the cylinder. So the parallels are, what do we want to say? Does anybody know what this one is? I think this is direct from your notes. They're straight lines. You can see the parallels. They go straight this way, right? But look at the meridians. Look at how the meridians are shaped. See how they kind of whoop? They kind of bend depending on where they are.
Cubic equation.
Yes, it's almost as if you took the paper off a globe and then tried to lay it out, right? This is kind of what you'd get. So now, some other types of maps are these topographic ones. All right, so topographic maps are going to show your elevation with, what are the lines called? Liam? Contour lines. All right, these are contour lines. So they never cross. So if you have a look at these contour lines right here, I'll zoom in a little bit. So see right here where this one makes a complete circle and it's the smallest circle inside of all the other circles? What does that mean if you're looking at it?
The highest,
Piper,
that's the top.
Piper.
That is the highest point.
That's your highest point. Very good. So Piper gets that. It's your highest point. Now, what does it mean that these lines are super close together here? What can that tell you, Drew? that it's steep, that the
That
distance.
Don't want to fall down it.
Right, so basically what this is telling you is, the distance between these lines is it describes basically a change in elevation. So when the team had supercalifragilistic had the driveway, right? And they made a determination of how many feet it's a meters in elevation there was, right? From the bottom to the top. They did a really smart thing to estimate it too, super smart. Now, if they decided to get really specific, they could take multiple measurements from the bottom to the top and break down, like if they could walk every 10 feet or whatever, every 5 feet, decide that's your unit, measure again, because definitely our driveway has a steeper point, like it's less steep and then it's steeper. And you would see that reflected in the way the contour lines work. So measuring steepness, that's going to be, we already did that one. So that the closer the contour lines are together, the steeper the slope of the hill, right? That's what Drew is saying. So if the space between the lines stays the same, then the slope is nice and constant. So this is what you want if you're building a stairway, for example, outside, if you're building stairs, like on a hill. Wouldn't it be nice if it was nice and constant? That's great. That's nice and comfortable. So stream flow direction, you can see where streams are. So when contour lines cross valleys, they form this V shape, and the V always points up the hill. So you can use this to determine the way water will flow across an area depicted on topographic maps. So see the V's right here? That's where the water, there's the water right there in between the V. All right, and then also contour lines form irregular, anybody know what it is, Bailey? Shapes is close, what shape? Yeah, they're irregular circles, right? They're these kind of, go away, why are you not going? Oh, there, they're irregular circles. They do connect somewhere, sometimes very far away, but they do connect. So it is a circle, and they are concentric, one inside of another, inside of another, inside of another. They go this way, right? And the elevation between the lines, contour lines, is never higher than the value of the higher contour lines. Basically what that means is if you're doing 500 feet and another marking at 600 feet, there could not be a point where the elevation is 650 feet without another contour line. So it always lets you know where you're headed, going up, going down, whatever. These are super useful if you're hiking, right? So geologic maps. All right, so this is a geologic map of Georgia, and you can look at it online. It'll pull up pretty easily if you put in Georgia geologic map. So basically what this shows you here is the location of certain minerals. So geologic maps show types of soil, types of rocks, locations of minerals, locations of metals, locations of precious gems.
Looks like everything's up at the top.
There's a lot up at the top. Why might that be? Sky. There's mountains up there. What does that mean for, like, Sky? Why do you think that is that might cause them to be located there? Yeah, there's more stuff, right? There's more mass because it goes up higher. And also because the way the mountains were formed, ours were formed in two different ways. They're formed primarily by the plates kind of crushing, right? So that shoves all the stuff that made it spread out into one area. And then there's also some areas that have had some glacial carving as well. So does anybody know, see this area right here where it kind of goes from mountain to plain? Does anybody know what that's called? Runs right through Georgia, do you know? Nope, do you know? Yeah, well, it's not a plateau. It's actually, they call this the fall line, and it runs through Georgia, through South Carolina, North Carolina, into the bottom of Virginia, but it's basically where the mountains meet the plain on the east coast of the United States. So it's called the fall line. And there are actually some people that like live along that area where they have, it'll be called like, fall line cheeseburgers or whatever when you come by. So that's kind of like the geologic name for that area. And when you're driving through it, it's obvious that things are changing rapidly. So we're kind of in the foothills area. We're not quite in the mountains, but we're in kind of where the mountains start because, so anybody know what the AT is? The AT? Appalachian Trail? Yeah. Does anybody know where it starts? Where?
Georgia?
Yep. Good guess. It starts in Georgia.
I think of the specific.
Yeah, up near like I think Unicoi.
Yeah. that's where-
Yeah. So if you So I have a friend right now who's actually hiking the AT. So a lot of people do this, it would be like a life goal, and he's young and, you know, he can do it now, because I guess, you know, whatever, he doesn't have all his other responsibilities yet, yeah. So, basically people hike it and they camp along the way, and you can hike from Virginia to Maine. It's a great movie, I can't remember what it's called, I'll have to look it up for you, but, it involves a big, long hike through the AT.
Just at Unicoi, that's what I was trying to think. I was like,
mhm.
it's just-
Yeah, so we are here in this area, we have hills, right? When you drove into the neighborhood, you go up and down hills. Where I grew up, I was at sea level, because I grew up in Virginia Beach. So we had no hills. It was just, I mean, flat. There was one neighborhood that had a slight hill in it. And I'll tell you this funny story about it when we get to the elevation thing here. So another type of map here, oh, and one more thing about this map, this guy here. All of these are explained in a key. They all have a code, but it's different types of minerals. So it's interesting.
Like iron.
Yeah, iron, quartz. Georgia in particular, North Georgia towards the mountains is famous for pink marble. If you didn't know that, we're actually a big source of pink marble. There's a pink marble house up there that was owned by the family that owned like one of the original mines. It's gorgeous. It's really unique looking. So yeah, and we have also got obviously gold. A lot of it's been mined out, but if you've ever been to the gold mine in Dahlonega, anybody ever done the gold mine in Dahlonega? We did it, the last time I did this class, we did it as a class and it was super fun.
We go like.
Mhm.
every-
It's weird, it's under the Walmart. Yeah, because the Walmart's been built since then, but it's a vein of quartz and the gold fills in the cracks and the holes within the vein of quartz. So if you're looking for gold, quartz may be something you're also looking for. So bathymetrics, so these are a type of topographic map with contour lines, but they represent the depth of a body of water. So sometimes if you're in a boat, like if you rent a boat or whatever, you own a boat, you can see a little map like that on the screen that tells you how deep the water is below you, so you don't run aground or get your motor stuck in sand or whatever. So the numbers are low near sea level, become higher with depth. And these are, we'll show you some of the methods they use for building these, but these are useful if you're obviously running a boat through. If you're running a barge through an area or a big boat, like an aircraft carrier, you need to know how deep it is, right? Do you guys remember when that container ship ran aground in Savannah a couple years ago, started sinking? With like, it was from Korea, I think. It was full of Kias and I don't even know what else. Yeah, it was a big deal. Yeah?
We read like an article and there's a bunch of invasive spiders.
Oh, the Joros? We talked about them last year. Yeah.
Yeah, we got a bunch of them. at our house.
They're not as bad this year. It seems, not on everything that's wood. But yeah, we talked about them last year. They're from Vietnam and a couple of other countries in the Southeast Asian area. And they are, yeah, that's an invasive species. So we talked about them last year in biology because we could actually go out in the woods and see them. I actually went around. I'm all about let things live for the most part. Like if I can catch something in this house, unless it's one of those palmetto bugs, those I don't mind killing. But if I can catch something in this house and let it out, I will. I tried to get a spider in my bathroom the other night. I had a jumping spider. And as soon as I get close to it, it ping, and I'm like, where'd she go? But I got video of it because it has, they call them white flag waving. I can't remember what they're called. They have little like white on the end of their little pedicles. They have these little white spots and they do this at you. So it looks like they're waving with two little white. But I tried to catch him. My point is that, yeah, my point is that he didn't surrender. I saw him again this morning. So my point is, if it's inside my fence line though, and it's one of those Joros, I'm gonna get rid of it because they're invasive. They're not good for this area. They're causing all kinds of ecological issues. So Caitlin, if you want to grab one of those folding chairs from the other room and bring it in or whatever, you can. So anyway, I went out there one day and I sprayed 37 of them within my fence line. They were super invasive. Yeah. So watch out for them. All right. So map legends. Let's talk about that. You've seen these before, right? These are super helpful. It's ridiculous to try and write everything on a map. You wouldn't be able to read the map because there'd be words everywhere. So like around the corner from here is Chattahoochee Point Park. It's not like Main Park or something, or Central Park. It's Chattahoochee Point Park. If you wrote all that out on a map, you wouldn't be able to read it because it'd be too much mess. So they just put a little thing as park and then you look at the key and go, oh. So all kinds of things show up on legends. Obviously things like streets, roads, railroads, but then you can also get stuff like restaurants, stores. And you know, if you've used your phone that you can type some of that in and it'll show you one thing and then show you another thing. Like we looked at bike trails versus streets versus MARTA. So Those are, without them, the map would make no sense. Now scales, you got three main types of scales. You got a graphic scale. That shows you a little image. So you got 0 kilometers, 5 kilometers, 10 kilometers, and that gives you kind of a distance. So if you're measuring on your map, like sometimes if you're really picky and you're trying to get some very specific information, you could get a ruler out. But if you're just trying to like look at a map and get a quick idea, what a lot of times people do is they'll put their finger down and they'll go, okay, well, you know, the length of my fingernail from here to there is roughly this 1 centimeter. So I'll just kind of measure it out, right? People do that all the time. So a verbal scale is going to lay it out for you. 1 centimeter equals 1 kilometer. And this last one, you get a fraction. It's really, what is that when you have a colon between two numbers?
Ratio.
Yeah, ratio. Okay. So what do you suppose that means? 1 centimeter is 100,000 kilometers, or it could be 1 mile is 100,000 miles. It's just saying whatever the unit is, that's the fractional ratio. So if you ever tried to, has anybody ever tried to make a scale model of something? And you have to, have you done, yeah, Drew's been making planes out of paper, and he's made scale models of these planes. So in order to do that, you have to do some math, and you have to basically use a fraction or ratio and say, okay, if the real plane is, like, how long roughly are they from nose to tail? An idea. 70 feet. Okay. If it's 70 feet from nose to tail, and I need to make it roughly this big, what am I going to need to divide by with every measurement I take so that they're all within scale? So I do that a lot when I do cakes for people, because I've had to do cars and planes and things like that on cakes where I have to basically find out how big the real thing is and then just start dividing down until I get it roughly right. So those are the three ways you can represent scale. So remote sensing, this is how we've gotten good at finding out exactly where things are located. So in the past, it would be some dude on a boat, some cartographer guy, right? That would be cartographer, a map maker. And he would look at he'd sail along the shore and he'd draw it out and he'd go, oh, it was roughly this shape. If you've ever seen like really ancient maps, sometimes they're like way off. You're looking at them and you're like, what in the world? Like the shape of Australia is strange or something like that. Because they're doing their best, really, just kind of eyeballing it. And they take measures. They'll go out and they'll survey from one place to another. Like George Washington, do you know that he was a surveyor, right? Like, and you've probably seen them. Like they still do it. They have that tripod and the little thing on top, and they measure from one place to another. So those guys are surveying, and that's what they're doing, is getting accurate measurements. But now we can do some remote stuff. So we have Landsat, and Landsat basically is a bunch of satellites, and there's this reflection of wavelength between the satellite and the Earth and back, and they can sense the topography of the Earth. Does anybody know what year that started? Alex knows what year.
I'm gonna guess 2006.
2006 to present. Anybody else want to guess? Liam?
1976.
You're closest, 1972. So if it were 1976, it would be as old as I am, but it was 1972. It's actually older than me. So we've been doing that for a long time, bouncing our data back up, bouncing these wavelengths back and forth so we get a good idea. Now we have this TOPEX Poseidon, which they stopped in 2006. This one's a radar, and it's helpful for things like oceans. It's used by NASA, and this one here, CNES, this is, I think, France's version of NASA. It's one of the European countries. I think it's France. Anybody know what year we started that one?
1992.
92, what do you think?
Somewhere in the 80s.
Somewhere in the 80s?
84.
84, so 92. Ah!
I'll go
You
guess.
know, yeah, so 1992 to 2006, we were doing this. So this was big stuff. This was super cool. Ooh, look at that. And you can see the kind of images it created. So next we have this thing called C-beam. All right, this is done with a boat, and they go through and they project. This is all sonar. So they're using sound waves, right? And they're bouncing. It's like ultrasound when, like Miss Jackie will get an ultrasound of that baby and just bounce the sound waves back and create an image of, oh, cool, you can see its little head or whatever. Same thing. This is how they find, a lot of times you'll see images of like shipwrecks and stuff. And that's from this sort of technology. Does anybody want to guess when that started? Ooh, I love the guesses. I love the guesses. Piper?
1982.
82, Alex?
74.
74?
65.
65, 77, you're close. So there you go. So they've been doing this for a good while, bouncing off the bottom of the sea or the lake or wherever you are to get an idea of the topography of the bottom. So global positioning system, this is our GPS, right? When did that start? Piper?
2000?
2000s, Alex? Yeah.
Trying to think, when did we land on the moon?
69,
Okay, I'm gonna go.
Is that real though?
78.
78, Caitlin,
82.
Chloe,
90s.
90s, James, Lily, 70s, you think,
75.
75, Jack?
I'm less confident.
69.
I mean,
I think
Sure,
it's after the
69.
moon.
Okay. So 73, right?
Close.
You were very close.
I was also. close.
That, yeah, James is close too. So this is,
79.
that's when we started GPS. Now, obviously, it didn't become ubiquitous for your average citizen until much more recently. And so pretty much everything that you use these days in your day-to-day life is some type of GIS, okay? So a GIS over here is your geographic information systems. What this is it combines information and it manages it, analyzes it, and it's connects data to a map, integrating location with the types of descriptive information that's there. And it provides a foundation for mapping and analysis that's used in science and almost every other industry. So how does GPS work? Okay, how many satellites are required for GPS to pinpoint your location? Anybody want to guess first? Drew? 3? 5?
A bunch.
A bunch?
for some reason,
3?
I'm thinking 6.
Okay, so let's see.
Yes.
Hopefully this one doesn't bounce around as much. Let's see.
Believe it or not, we use GPS devices
I'm personally
to
thinking.
use
so you better set
stars. So that thing that tells your phone exactly where you are is actually similar to how ancient sailors navigated the dark, forbidding seas. Those constellations of the night sky, they helped us locate where we were by giving us a
I'm sure
reference.
that's exactly how.
GPS, the global positioning system, is a network of about 30 satellites in the Earth.
Well, wait a minute, it says how many there are.
That act like stars, giving us similar reference points to help locate us down on the Earth's surface. Of course, those rusty old sailors would be shocked by the accuracy with which we can do this now. At any given time, at least 3 of those satellites are overhead of anyone on the Earth. Those 3 satellites locate a
What's that?
receiver back on Earth.
I was right.
Communicate between one another with radio waves. Then they calculate a 2D position between them using our latitude, longitude, and by tracking our movement. With 4 or more satellites, air traffic controllers can determine the pilot's 3D position. That also includes altitude. So the next time you're geotagging a selfie or flying back home, remember that it's those 30 satellites above us that work like the stars in triangulating your exact position while you sleep. The United States Air Force is powered by airmen and fueled by innovation.
Woo, Air Force.
To learn about how stealth planes work,
Oh, very cool. Stealth planes are cool.
When do we get this?
So, who uses Waze here regularly? I use it almost religiously. What's different about Waze compared to Google Maps or Garmin or anything else that's gonna like give you directions and tell you where to turn? What's different? What is it, Melo? It's more reliable. Why? It can show you back ways, but so can Google. What, Liam?
Little icon's cuter.
The icon's cute, okay?
That's so much more handy.
You can like report accidents.
Aha, she's got it. Okay, you can report stuff on it. So we're integrating something else. We're integrating social media into this map system that's already using road maps, photographs, GPS, all that kind of business is all integrated into one system. It's all managed by one system. And then you're driving along and you see a crash and you go tag accident. You don't do that on the other one. So this one involves social media. And that's what makes it different. That's super cool because this tells you where the cops are, you know, like where the cops are, where the accidents are. Anybody ever tagged animals? I've tagged animals. The other day I was driving down the interstate and there were like 2 bucks on the side of the road. And I thought, oh, that's not good. Because if they come out in the interstate, that is super dangerous for the bucks and the humans. So I'm tagging animals. I didn't even see people on the side of the road. There's nothing in there for people. So I tagged them as animals because they are animals on the side of the road. I've done it many a time, like animals. And then people can comment and say, thanks so much. Or if you're stuck behind an accident, you can take a picture of it and upload it to Waze so the people behind you can see how bad it is. I mean, all that is integrated. So that's why Waze is very, very interesting. So Waze is a GIS, Geographic Information System, using ArcGIS. So that's Aeronautical Reconnaissance Coverage Geographic Information System. So ArcGIS is a family of, here we go, here's the technical talk, client software and server software and online geographic information systems services developed and maintained by S3. Drew, can you make sure that's not anything important? So ArcGIS was first released in, anybody want to guess? ArcGIS, not Waze specifically. You guess? Anyone? Go ahead, Alex, what's your guess?
97.
Ooh,
2005.
2008.
How about you guys back there? 2000? Just yell it out.
88.
88, okay. So 1999. So your 2000s were real close, right? So
We're going by Price is Right, you got over.
ArcGIS Online is cloud-based mapping analysis solution. And the cool thing,
Nothing's there, there's no package.
Ding dong ditch. It's a ding dong ditch.
where's Ozzy? Is Ozzy inside? Can anybody see him?
Oh, there's people up.
Yeah, it's the guy doing the lawn. I just want to make sure Ozzy's inside. He's over there. Okay.
Some got a dog or a-
No, he's probably downstairs with my mom, then that's fine, as long as he doesn't go, yeah, as long as he doesn't go out there, because he won't be there. If he does, we'll all hear about it, right? Okay, because he's loud, yeah. Oh, I've, the best thing, I'll just show you the cat video. We chased the cat, Drew was mad, we chased the cat, it was fun. So longitude and the chronometer. All right, so throughout history of navigation, latitude could be found relatively accurately using celestial navigation. So we're using our stars, right? However, longitude could only be estimated at best. And this was because the measurement of longitude is made by comparing the time of day difference between the mariner's starting location and new location. Even some of the best clocks in the early 18th century could lose as much as 10 minutes per day. That's a lot. Which translated into a computational error of 242 kilometers or more. Is that him? Oh, okay, well, that's amazing. Ozzy, come on sometime today. Let's go. Please.
I
Please,
have
right
short
there.
legs, like.
Thank you. You wait there. Thank you. I don't want you to tag me in. Thank you. Okay, so think about that. If you have a computational error of 242 kilometers, what at the equator, what was and the equator is where you're gonna have the largest distance between your meridians. Does anybody remember how many kilometers? You remember, James? Do you remember? 111, correct. So if your longest possible distance is 111, but you have computational errors of 242, can you see why that would be a big problem? Like a really big problem.
Off by 32 infinite kilometers.
Yeah, it would be a giant mess, basically. So in 1764, British clockmaker John Harrison invented the seagoing chronometer. And this is the most important advance to marine navigation in the 3 millennia that open ocean mariners have been going to sea. Huge deal. And the reason it's a huge deal. So in 1776, you had this British dude, you probably heard of him, Captain James Cook. You heard of James Cook? He's a big, important guy. So he used this chronometer that Harrison invented to circumnavigate the globe. And when he returned, his calculations of longitude based on the chronometer proved correct within 13 kilometers. That is way closer than 242 being off. So a margin of error of 13 is nothing. Are you guys okay back there, Milo Parker? All right, so a margin of error 242 is a way bigger deal than 13, right? So it's much more accurate. So from the information he gathered on his voyage, Cook completed many detailed charts of the world and completely changed the nature of navigation. Also made maps look way more accurate. Some of those weird distorted things are a whole lot less distorted. So in 1884, by international agreement, the prime meridian was located in Greenwich at 0. That's when everybody kind of came together and was like, okay, I'll stick it here. And really, when the British people are, in 1884, they're trying to hang on to whatever power they got. So they're like, hey, we're in charge. We have the Captain Cook and all the other good people. And they go, okay, we'll put it in Greenwich. Anybody ever been to Greenwich? No, last time I was in the UK, I wanted to go, but I didn't get it.
One of my favorite map disputes was here, and you can go to oversimplified and look up the pig war, it'll tell you, but it's like, they went from like this line.
Mhm.
And like, I believe it was where like North Dakota is now, or something like that. And there's this lake,
Mhm.
and they went from the most northwestern part of this lake. But the lake wasn't like that,
Oh my,
it was, they pretended it was more like an oval kind of, but really it was like a lot of the lakes are, it was like
right,
branchy and all that stuff.
weirdly shaped, yeah.
Yeah, so basically they straight lined it to, Washington,
Mm,
and then
yeah,
what was left was the Vancouver Islands.
yeah.
So they had to figure out what was that, and then,
Well, you had like Leif Erikson stuff, and his maps of like Greenland and stuff were really weird looking. They called it Vineland at first, and then it got all confusing. Vikings did all kinds of fun things, you know, that whole group of people.
yeah, and then Britain and America went to war. with
Right.
big.
So let me ask you this, how do we determine elevation? What do we measure it in scientifically? Do you know, Drew? Well, meters, but what's the unit? Meters, like how, what are we comparing it to? Wait. Yeah, sea level. Okay, very good. All right, sea level. All right, we're comparing it to sea level. So sea level is, you got all the water in the world, and there's some point where it kind of levels out. Now it shifts because of the moon and some other factors, but you primarily have an area that you're going to consider this is sea level, and we put that at 0, right? And then everything else is going to have an elevation slightly higher than 0. So like I was saying, where I grew up in Virginia Beach, it was pretty close to sea level for most of the area because it's at the beach. We didn't have, there were no hills. So there was this one neighborhood, it's not far from the ocean front, and there's a golf course there. So they built a lot of hills in for the golf course, but there actually was like one natural kind of hill. Don't know why, maybe the dunes formed there, but there's a little hill and one little hill, it's probably nowhere near bigger than the one you do on Sterling when you come down here. That one, it was half that, right? And so my best friend called me when it was snowing there last winter, and she's like, we're sledding on Christmas Hill. And I said, where the heck is that? I mean, I grew up here, I don't know what you're talking about. And she said, oh, well, it's kind of newer. So she took a picture, and I immediately knew where she was. So I was like, oh, you're off Holly Road. I know that house because it's a very unique looking house. And she goes, yeah, they let us sled in the backyard on the golf course. So she sent me a video. Okay, so the kids are starting at the top of the sledding hill. Okay, these are beach kids. Sledding hill was, okay, if it started at me, it ended at Bailey. And I think the drop was maybe 8 feet, not even, probably closer to like 6 feet.
One of those
So it's
shelves
like
to
going
down
from here to the floor over a distance from me to Bailey. It's nothing. It was nothing. And they're all like, whoa, these beach kids, they go, "Meow," and then they just stop and they think that's the best thing ever because that's the biggest hill you're going to get in a place like that. It was pitiful is what it was. I texted her back. I'm like, you can't count that as a hill. I mean, that's really sad.
That's a bump.
Yeah, it's a bump. Uh-huh.
One more thing. My grandparents' neighbors
Mhm.
had a driveway that was like this, so. like, but their driveway was like kind of off-centered with my grandparents' driveway,
Mhm.
and my grandparents' backyard has a lake
Oh,
down under it. So
okay.
they started at the top of their driveway, managed to move their sleds to my grandparents' driveway
Wow.
and skate all the way down, and there's like woods in between the lake and their backyard. And
With the
step-
trees,
Yeah, and like.
like Clark
somehow-
Griswold. Yeah.
No trees, nothing.
Right.
It was amazing.
Impressive.
That was during that one big snowstorm.
When
like,
we had the
what?
snow this winter, we actually got, my husband has the GoPro 360, so you can hold it out and the stick disappears. Its software takes the stick out so you can see 300. You can move the camera around on your screen and decide what you want to look at. It's really cool. But my neighbor held it and they slid down his backyard, and it was hilarious. He had a great time. So in a place like Virginia Beach, where I grew up, where there's like no elevation, the highest point in that city is this place called Mount Trashmore. Trashmore. And it is literally the original city dump. And they built all the trash and they piled it up and they compacted it, and then they covered it in dirt and planted grass and made it into a city park. And you can see it from the interstate. It's right next to the interstate. It's not even a mountain technically by height. It's a hill. And you can run up it and run down it. It's not that big of a thing. It's just this perfectly green mound. It kind of is one mound with a slightly smaller mound off to the side. The city seal is right on the front of it, just right there. You can't miss it. But when I was a kid, there was a period of time where they were concerned about the structure of the mountain because, of course, it was made of trash. And what happens to trash over time? It starts to decompose. And what gets produced when microorganisms eat things? Yeah, and yeah, all
Methane.
kinds of gas. Methane in particular was one we were concerned about.
Explode.
They thought it would, so they drove big pipes way down into the mountain so that it could let the gas out so that it would blow up, which would have been interesting because then you would have had like a mountain blowing trash dirt all over the interstate. So that's the other place we would go sledding, 'cause that's an actual hill. I mean, it's like, so it's man-made and it's the largest, it's the highest landform, right? So here we've got, the height changes rapidly from 1 yard to the next, right? Because we're in the foothills. So the area that is where I showed you before, past the fall line, where it's nice and flat. What do we call that kind of landform where it's perfectly flat? Anybody know? James? That's a plain. That's good. So when you've got a landform that is perfectly flat, that's a plain. How about if you have a landform? So relief is like a measure of steepness. Okay. So that would be very low relief. If you have a landform that has very high relief and the landform itself is high, then you have a mountain, right? What do you call the thing where it's like a mountain but it's flat on top? What's that? Let's say it. Somebody say it.
Plateau.
A plateau, right? Okay. What is the word for table in Spanish? Who knows? Do you know? Mesa. Okay, very good. Ever heard of a city named Mesa? Arizona has a Mesa, Arizona. That's another word for plateau. If you're Spanish speaking, that's your plateau word.
In Minecraft, there's a biome called the Mesa Plateau.
Okay, well, there you go. Because a mesa is a table and a plateau looks a lot like a table. Right. So one thing that concerned me when we first moved here is, so this is the Chattahoochee in my backyard, right? So the Chattahoochee starts north of Lake Lanier and then it spits out of Lake Lanier at the dam. Why does it do that?
Because humans built the dam there.
Because humans built the dam there, right? So Lake Lanier was built in what, the late 60s, I think? And why was it built? Does anybody know what the purpose of the dam is in Lake Lanier? Do you know? It's a power plant. It's hydroelectric. Okay, so
So money.
if you drive across, well,
There's
and
also a
power
city,
people.
like,
So if you drive over the dam, you'll see all of the infrastructure for power. You'll also see the goats. The goats are out there eating the grass because it's hard to mow on a hill. And it's very steep because it's a man-made dam. So what's under the lake?
a city.
You know? Did your hand go up? Anybody know what's under the lake? Yeah, do you know? Yeah.
City?
It's a little town under there primarily. There's a lot of things, but anybody know the name of the town that got flooded?
Lanier?
No, Lanier is Sidney Lanier. He's a poet laureate. That's what he's named after. So it was Oscarville. And that's the town. Now, if you look at maps, you'll find certain roads like, I think is it Driscoll Road, and there's a couple of other ones up there that you can see the road start on one side of the lake and then it ends up on the other side of the lake. And then you can see the ferry roads like Shadburn Ferry or whatever is way over here in Gwinnett, and then you see it again over here in Forsyth. But and then those are the ferries like that's where they actually used to send people across on a boat because there was not a bridge, right? So there's Nesbitt Ferry and there's a bunch of ferries. McGinnis Ferry, that's just the name of the family that owned the land and ferried people over. So what concerned me when they built the dam and we moved here to this house, right? So there's a river. So I thought to myself, well, what happens if something bad happens to the dam? Like the whole lake's coming, right? So because we're slightly further south from the mountains, the general elevation is higher up there. So if the whole lake came out, am I gonna be swimming? Or like I was kind of worried about it. So I went online and I was able to get the distance from sea level at the lake, roughly sea level here, how many feet that was, and then the distance from like my level backyard across to Gwinnett, where that gets level. How big would the river have to be wide and how big deep would it have to be? And basically, I don't think I'm gonna flood, which is good. But those are all measurements that you can take and figure stuff out. It's fun. So looking at your binder work. So leave this up for a second and let you look. And then I'm gonna go over to our test. We have tests, right? So we have stuff to study for. And then I'll make sure that you guys have these with your notes. So this is what Lily was showing me a minute ago. This was really hard to try and put in on the computer. I didn't want to do it letter by letter, but I almost wrote it instead because so these letters are all kind of funkified because it's hard to place them in there.
I see Ts that are crossing into oceanography.
Yeah, the spacing was difficult and I mean, it's ridiculous. So unit 1 test study topics. All right, you know that this little image will show up. Where will you find it if you're looking for your test study topics? Ready? Dropbox. In what folder?
Slide.
Not in slides.
Test
It
study.
says resources. And when you go in there, it'll have tests, right? And then you will find these little study guide things in there. It'll tell you exactly what to look for. Now, I don't put stuff on tests that I don't tell you is important enough for you to really study and commit to memory. Some stuff is just interesting stuff. It's additional information. You can't possibly be tested on every single thing we cover. It's too many things. I tell you what I feel is the most important stuff for you to know. So these are the things I think are most important for you to know. So looking at the first one, who can explain or expound upon controls, independent variables, dependent variables? Jack, you want to explain for me?
Control variable is what you keep the same.
Mm-hmm.
Independent variable is what you change, and dependent variable is what you observe.
Yeah, that's perfect. That's exactly right. And why is it important to have a controlled experiment? That's like 2 questions down, but it's kind of related. Piper?
So have something to compare the results to.
There you go. That's really, really good. You don't want to change a bunch of variables because it's ridiculous. All right.
Makes it easier to determine if it's actually causing it.
Absolutely. Okay, so looking at the one that says formal, social, and natural sciences. Anybody want to give, what do you think that's about? What do you think you need to study there? Right, Bailey?
Different branches under those.
Mm-hmm. What's the difference between what is an example of the formal sciences, social sciences, and natural sciences? How would you define it? No, Alex?
Formal sciences has math and logic. and
Yeah.
everything. Social sciences is more study of human behavior,
Mhm.
and natural science is just about everything else.
That's right. That's right. Yep, very good. All right, so what makes a good hypothesis? Drew, you give it. Go ahead.
I thought something that could be, something that could be tested and it's either.
And repeatable.
And repeatable. So a hypothesis is an idea that can be tested. You have to be able to repeat the testing, and then your results either are supported or rejected. We don't say proved or disproved. We don't say right or wrong, right? Okay, so metric conversions. What do you think you might need to study there? What do you think, Bailey?
The different, how much things to get from one to the other.
What does it always, by what unit are you always moving? By 10, they're always moving by tens from one step to the next step. You're either multiplying by 10 or dividing by 10. And how about the units and the prefixes? Piper.
King Henry died drinking chocolate milk.
Yeah, King Henry died, and then there's the little one in the middle, unusually, or whatever, that's your unit. Drinking chocolate milk. What's the K? Everybody.
Kilo.
Kilo, what's the H?
Hecto.
Hecto, what's the D?
Deca.
Deca, and then you get a unit. What's the unit for mass?
Grams.
What's the unit for weight?
Newtons or grams.
There you go. What's the unit for volume?
Liter or meters cubed.
Liters or meters cubed. What'd you say, Jane? And how about length?
Meter.
Meters, good. Okay. Area.
Meter squared.
Okay. What's the next D?
Deci.
Deci, then?
Centi.
Centi, then?
Milli.
Milli. Okay, good. And then obviously it keeps going from either direction.
Nano.
Nano. So how many decameters are in a meter?
0.1.
How many centimeters are in a meter?
100.
Okay, good. So you can always just write it out and count it. So if I were doing that, and there were a lot of those questions, and I'm not saying there are, but if there were, and I'm taking this test, it's not already written on the test because this is a computer test, right? I would get a piece of paper and I would just write it out so that I could just count, just tap back and forth. That's way easier to do. All right, how about theory versus laws? It's one of my favorites. Let's see. Ah, Chloe.
So a scientific law says like how something's gonna, or what's gonna happen.
What is gonna happen? Okay,
And the theory is more of like a question.
the theory is the why. Mhm.
Why?
So scientific theory, well, we'll do it the other way. Scientific law tells what happens or fact, right? Scientific theory tells why it happens.
A theory.
Yeah, an idea about why, an explanation is what we say. One's a fact and one's an explanation. All right, Earth's relationship with systems. How would you describe that?
It's a system of systems within systems of other systems within systems of other systems.
It's
Complicated.
pretty good.
Within systems.
Yep,
Complicated.
concentric systems, inside and outside, right?
Systems and systems and systems.
Somebody give me an example. Okay, we're good. Somebody give me an example of a system that operates within the biosphere. James. An ecosystem. Yeah, okay. Back and something in the back. What's something that's going on like a cycle?
Trees,
Mhm.
they drop their leaves.
Yes. Great. Perfect. Bailey, do you have another example?
You and trees.
Water cycle. Very good. All right.
You and trees.
What is an example of a system within which the Earth resides? Ooh, Liam.
Solar system.
Oh, solar system is one. Great. Okay. How about closer to Earth? Piper? No?
What do you mean by closer to Earth?
Closer than the solar system. What's another system that Earth resides in that's closer than the solar system, Drew?
The moon and the tide.
Okay, that's the lunar. Yep, there's a lunar system there. We think, Alex?
Seasons?
Yeah.
One moment, I had some,
How about,
atmosphere?
yeah, that's what I was looking for. Atmosphere. Okay, that's a great
It
one.
is.
Okay, so relationship between living things and their environment. There was a very specific little bit about big ideas in earth science where we talked about the relationship between living things and their environment. Does anybody remember what it was specifically? Alex remembers everything. Anybody? Okay, what about it, Alex?
Biosphere?
There's a biosphere, but what's the relationship? Like, what's the relationship between the frog and the pond he lives in?
They both change each other.
That's it, right? So one, the living things impact the system in which they reside, the ecosystem in which they reside, and then that ecosystem also impacts the living thing, right? Back and forth. All right, so how about inference versus observation? Who can tell me the difference between an observation and an inference? Bailey, what you got?
Observation is something we can see or-
Guys, hold on.
Inference, you don't have as much information. You can still see.
Kind of.
Yes.
Yeah, you got observation spot on. What'd she say, Alex? Liam, you didn't know what she said because you were chatting. She's
Observation?
observation. She said that it's something you can see, hear, smell with your senses. Inference, Drew.
To prior knowledge.
Prior knowledge, that's exactly what we're looking for. So an inference is when you use prior knowledge. So you're looking at something and you see something going on or you hear something going on, but you're going to use your prior knowledge to explain it. So for example, in my old house, I would hear this and feel this strange rumbling every so often.
Earthquake.
It wasn't an earthquake, but if I drove about a mile from my house, there was a quarry. So the next time I'm in the house and I observe that rumbling, I can infer that what?
Someone blew something up.
They're blowing stuff up at the quarry. Absolutely. That's exactly right. Yeah, you can infer from what you already know. All right, what is energy's relationship to the cycling of matter? All right, Bailey.
Energy is required to do the cycle.
Energy drives the cycling of matter. That's exactly right. So keep in mind, well, we're gonna get talking next week about conservation of energy, which is one of our big laws, right? So, guys, put them down on the table, please. Second day of class and having to fuss people. That's not good. All right, so the constant nature of chemical and physical principles and their relationship to change. What is true about chemical and physical principles with regard to change? What do you think, Drew?
Formal sciences?
No, they're not. It's part of the natural sciences. Let me ask you this. What's an example of a chemical principle? James? It's hard to describe sometimes, isn't it? That's okay, Alex. Do you have a chemical principle?
Conservation of mass or energy.
Okay, yeah, but give me a specific example of a chemical principle.
Photosynthesis, I think was used as an example.
Could be. What were you gonna say? Yeah, how about, I'm thinking very specific. How about the way something smells? Is that a chemical principle?
Yeah.
How about color? Is that a chemical principle? Oh, it's chemical. Because if you think about signs of chemical change, it includes change of color. It includes change in temperature. It includes evolution of gas. It's cold stuff. So all these things are chemical principles. So those things are unchanging, right? Chemical principles are always going to be the same. How about physical principles? Are they always going to be the same? Physical matter can change form, but the principle is always going to be the same. For example, like the temperature at which something changes, right? These things are going to be the same. So your chemical and physical principles are not going to change, but they drive the changes you see in the environment.
Technically, with different atmospheric pressures.
Different
the
atmosphere,
melting
yeah.
and boiling
Right.
points will change.
Right. But if you really get deep into that, the principle behind it still hasn't changed. You just got to get deep into it. So yes, so your chemical and your physical principles are unchanging, and those things actually drive change because you can rely on the unchanging things to affect change, right? If you know that, for example, your stainless steel kitchen knife is harder and denser and more brittle and more rigid than your apple, you know that if you drive that knife into that apple, it's going to change that apple from, an apple to pieces of apple. It's going to drive the change. There's no way that you're going to do that and then the apple's going to break the knife. Like, that's not how it works, right? So somebody talk to me about open and closed systems. What have we got there? Liam.
An open system is one that can share energy freely. A
Mhm.
closed system is one where two things only share energy between each other.
Mhm.
And an isolated system is where one thing cannot share energy with anything else.
Right. So which one of those is more of an ideal than a reality? Go ahead.
Isolated.
The isolated system. What's an example, the best example we can come up with an isolated system? Like, there's an example that's often used, and it's like, this is the best we can do. What is it?
Something in a vacuum surrounded by.
Yeah,
stuff
like
that would
in a vacuum
dissolve.
furnace, like one of those thermoses that's got the vacuum, what is it called? What do they call
Vacuum
those?
sealed.
No, they're called vacuum seal. What do they call that? Yeah, it's like the vacuum chamber. You know what I mean? My mom has a little bottle like that. She can put ice water in it. Like 2 days later, it's still freezing cold. It's really impressive because the outside of it obviously doesn't feel cold, because if it did, it would be exchanging. So yeah, so these are the important things. So when you go back, to study, look at your slideshows from your first lesson and your second lesson. And pretty much that's where you're going to find your answers, right? It'll make sense. Has anybody thought yet about final project? You have? What have you thought?
I haven't touched.
Ah, okay.
It's about trees.
Would I be allowed to do it over?
Yeah, if you can find a way to make that geologically sound, like describe it, because obviously it's something completely fictional, but if you can provide the data that would be accurate if it were real. Sure. That's fun. I like that. Yes, Miss Caitlin.
I want to do Sesame Street.
That is a great idea. Nobody's ever done Sesame Street. So I will do like I did last year. And I will put up like a Google Doc that everybody can access. So you can put in your topics, so we don't all do the same topics. That way, once a topic's claimed, it's claimed. Nobody's ever done Sesame Street before. It was so fun. Obviously, Cole did Uranus. It's just, and I did this same lesson, the same assignment when I was teaching at private school, and it was the same thing. Like, I didn't tell them they all had to, everybody had to be unique, and like 4 guys picked Uranus. And it was super, because I got to see report after report about how Uranus is full of gas, and it was super fun. Yeah, it was great. It's fun. It's
You
fun.
might make me pick.
Good times.
Great.
Really good time.
I can mark that.
So I'll give you one more parting thing, and then you have like kind of 10 minutes to gather up your stuff, make sure you're good to go. Be sure that you have turned in homework, okay? And be sure that, I have a winning Rico. And be sure that you, it was. This other stuff. Oh, wait. Huh? The homework to turn in, it's online. Couple questions. Where is it? It was Miss Caitlin. Was it Caitlin? Yeah, Miss Caitlin. And the reason that I picked Miss Caitlin is because of the flip flops, they won me over. The flip flops won me over. I'll send it to you, right? Yeah, you and you. Okay, so I'm gonna be a little lenient the first, like, maybe 3-4 lessons till everybody gets caught up. There's some people that don't have books yet. I get that, right? But you're gonna need to be sure that every week you're doing your binder work, right? And if you're answering questions in here, and especially like Bailey, if you've got the binder open and I know you're answering from the binder, I don't have a doubt that you did your binder work. But if I don't ever see your binder and I don't ever see you answering a question, I think maybe they didn't do their binder work. And I could always just walk by and say, let me see it, right? So your binder work, credit, yeah, you always do yours. So, but if you're not here, I don't need you to like send me every page of the binder. That's a lot of work for you. I don't need to do that. Just next time you're here, go, here it is. Okay, we're good, right? Be sure you do your homework. Be sure you do your binder work. Look at your syllabus. Look at. It tells you everything you need to do and when it is due, right? You watching my doves? Okay, that's the idiot woodpecker. Did you see him? Did anybody see him? All right, so he'll come back. So he's a red-headed woodpecker. He's not the big ones. The pileated ones are like the woody woodstock ones, right? This is one of my mating pairs of mourning doves. There's still, I can tell you who is who. I have like 2 or 3 mating pairs. Now that dumb woodpecker is too big for this bird feeder. But he comes, that's one of my baby male cardinals. See, he's not quite red yet. He's trying to be red. This nitwit of a woodpecker will come over here and it's too big to get on the bird feeder. So he hangs underneath of it with his feet and he swings the whole thing around and he's so big that he freaks everybody else out and they all leave.
Yeah, during lab, there was like 3 on it and then like all of a sudden it just shaked.
Yep. That's my girl on the rail. And that's the male on the, he's slightly bigger and a little thicker through the breast and the neck. And that's that little baby male cardinal. He's cute. Now, what's funny, I've noticed this. The doves will do something none of the other birds do. They will stand on the rail. Maybe she's gonna do it. Let's see. And they slide down for fun. Oh, no, she's trying to eat. Everybody's coming to eat. Ah, she kicked him off. Look at that. And I have a pair of bluebirds. That's the one. See that guy right there? I think he's got mites. Look at his head. Looks sad. But I have 2 different mating pairs of bluebirds. And when they first arrived 2 years ago, the female was so afraid to do anything. And the male would go ahead and mealworms out here and he would get mealworms and bring them to her. It was awful. So anyway, study. Test. You got it. Read your email, look at your syllabus, and you'll be good to go. Before I start dinging people. Ding, ding, ding. All right, get your money. Take your money and run.
Extra large.
Take the money and run.
Go on, take your money and run.
James, you can have Michael's.
Like Billy Joe and Bobby Stew.
I'm giving my points to Alex.
If you don't get that reference, then you're Alex does not need any points.
Here,